Once you have completed the longitudinal distribution of moments for each of the 4 rigid frames, the next step is to make the transverse distribution. For this, we will consider a factor which is called torsional constant C of the transverse edge beam. We will do a couple of exercises to find torsional constant C of beams. The formula to calculate this torsional constant C is this, where x is the shorter dimension of the component rectangles and y is the longer dimension. So I'll explain the concept what is a component rectangle here. For example, we have a T-beam here. We can analyze this beam in two ways. Either I can make it like this one, like I'll make this one as one component and this one as the second component. This is the first component. The other option for this T-beam is like this one. I'll make lines here, I'll make this one. So my first rectangular component will be this one. The second will be this one. And this will be the third one. This is the third one, this is the second one, and this is the first one. So I'm going to apply the formula which I showed you earlier here for these rectangular components, and I'm going to see which one of the two options will give the highest value of C. The highest value of C will be considered as the torsional constant for this T-beam. In the same way, if I have a rectangular beam like this one, so for this rectangular beam, I will calculate a torsional constant first by making a line here, making this as the one rectangular component and this one as the second rectangular component. The other option I will do, I will make the same shape beam here. I'm gonna make a line here this way. So this will be my first rectangular component and this will be my second rectangular component. So I'm gonna calculate C1 for this situation, then C2 for this one. Out of the C1 and C2, the largest value will be selected. Now let us do a numerical problem. This is basically the continuation of the previous numerical problem. The beams which are spanning in the long directions, they are 14 cross 28. The one which is spanning in the short direction, they are 12 cross 24. We also know that in each of the long and short directions, we have both interior T-beams and edge beams as L-shaped beams. So we will calculate torsional constant for each of them. Because we have in short directions T-beams and L-shaped beams, so both of them they have been considered here. This is for short directions. These are for T-beams and this is for L-shaped beams. So each of the L-shaped beam, if we consider this L-shaped beams, so I can either make a line here or I can make a line here, and then I'm going to calculate torsional constant for case 1, and then I'm going to calculate the torsional constant for case 2. The higher value will be selected for this. Similarly, we're going to apply the same calculation on this T-shaped beam. Here I just make a line like this one, making two rectangular components. And here we have three rectangular components in the second option, one by cutting a line here. So this will be the first rectangular component as we already discussed. So we're going to do an exercise for an L-shaped and a T-shaped beam. Because I already told you the beam in shorter direction, they are 12 cross 24. So all of them, these are all 12. You can see all of them, they are 12. And the overall depth is 24, sum of 6.5 and 17.5. This will be the overall depth, which is 24. And this is B effective, which we have calculated for L-shaped beams and T-shaped beams in previous examples. Now let us see this example for short direction beams, because short direction beams we have beam dimensions 12 cross 24, where 12 inch is the width and 24 inches the depth of the beam including slab thickness. So this 24 inch you can see here, this 6.5 inch plus 17.5 inch, the sum is 24 inch, and this 12 is here. This 29.5 inch is basically B effective, which we have already calculated. So knowing all these dimensions, we will gonna calculate torsional constant C. So for this beam, first I'm gonna make a line here. This will be my first rectangular component in this way, and the other one will be this one. This will be my rectangular component second. So first rectangular component, the one I just highlighted, this is first rectangular component, this is the second rectangular component. So I'm just gonna draw here the first rectangular component again here. This is the first rectangular component. So this one is the shorter dimension, isn't it? 6.5 inch, and this one, this is a longer dimension. So I'm gonna call the shorter dimension as X and the longer dimension as Y. So the formula is 1 minus 0.63 into X. There was an X here, so I'm gonna put this dimension, which is 6.5 inch for this first rectangular component, and Y, which is the longer dimension here, I'm gonna put 29.5 here. So this is the formula, plus the same calculation will be applied on the second rectangular component. I'm gonna draw the second rectangular component here. Like this one is the second rectangular component, as you can see. So it's very clear that this is 17.5 inches and this is 12 inches. So this will be X here, the smaller dimension, and this will be Y here, the longer directions. So 1 minus 0.63 into X. X will be shorter dimension, which is 12 inches, and 17.5 is Y direction. So again, we're going to calculate both of these values and add them. So after adding, the value comes out to be 8050 inch 4. So this is the first option. The second way, instead of cutting a line here, I'm just going to make a line here like this one. So now I have these rectangular components. This is a rectangular component and the other one is this one. So this is the first rectangular component and this is the second rectangular component. I'm just going to draw the first one again here. Be like this one. Here we have 6.5 inches. So, and the above one is not 29.5 inches because this is the whole 29.5 inch. So we need to subtract the width of beam, 12 inches from this dimension. So 29.5 minus 12 inches, it will give you 17.5. So the value here is 17.5 and this will be 6.5. So it's very clear that this is X and this will be Y. So 1 minus, look at here, this is the formula, 1 minus 0.63, this will be X and this will be Y, 17.5. Similarly, when you're going to do the calculation for the other rectangular component, the rectangular component 2, the X, it's very clear, it's 12, which is the shorter dimension, and Y will be this one complete. This is the Y. So it's not 17.5, it is basically a sum of 17.5 plus 6.5, which is the overall depth of the beam, 24 inches. So 1 minus 0.63 into X will be 12 and Y is 24 inches. After this calculation, the torsional constant is coming out 10,704. So you're going to compare these one. The largest is this one, so you're going to use this one. In the same way, the calculations have been performed for a T-shaped beam as well. This is for a T-shaped beams. It's no more different. I'm just going to explain one tricky thing that they have done here, because I told you that this is, once you cut a line in this direction like this one, so you're going to have one rectangular component here and this is the other second and this is the third one. You're going to have these one. So because second and thirds are very similar, so you're going to see that there's a 2 here, like, because they are same. This one and this one is same, so you'll multiply 2 with this one, and these calculations, these are for this one. This is the difference here. I hope the first one, this one is very clear to you, because you have a cut line here. This is a cut line. So you have a rectangular component going on in this one, and you have another rectangular component going on this way. So you have to calculate torsional constant C, which is coming out to be 9650. Once you come to the other situation, because now you have three rectangular components, one the bigger one and the two similar small one. So for similar small one, you're going to use 2, and the calculation coming out to be 11930. So you're going to use the bigger one here again. In the same way, the long directions, you will have L-shaped beams. Also in long direction, you will have T-beams as well. So in each direction, you have L-shaped beams and you have T-shaped beams. So for each of these 4 beams, we have calculated a torsional constant C. This we already have discussed, like each of the rigid frame is divided between a column strip and middle strips, and we also have a discussion like if it's an interior rigid frame, so each interior rigid frame is having a column strip and half middle strip on each of its side, like it's been bounded by half middle strip on each side. Whereas if you're looking at an exterior rigid frame, it will have a column strip at the extreme periphery and a half middle strip attached to it. We have already discussed how to find the dimension of this column strip, how to find the dimension of overall rigid frame, and then the middle strip. Everything was previously discussed here. This slide is basically explaining the overall concept, what we have done started from here. We first calculated the total factored static moment. You remember we calculated m naught. The first step was to calculate m naught, total factored static moment. And this m naught we calculated for rigid frame A, then we calculated for rigid frame B, then rigid frame C, and then rigid frame D. So this is a complete value, like this is m naught for A, because this is interior rigid frame A, so this is m naught for this complete one. The second step we did is the longitudinal distribution. For that, what we did, we distributed this total factored static moment m naught into 5 locations, like this one. This was for location 1, this was for location 2, this is for location 3, this is for location 4, this is location 5. Out of these 5 locations, we have already started that first 3 locations, they are dependent on the case, and onwards the values are taken for typical locations, 0.65 and 0.35 of m naught. Now once you have the longitudinal distribution, the next step is to have transverse distribution. So now for each of these 5 locations, for example, we already stated that this one, this is m exterior negative. This is for the location 1, so you have to distribute this m exterior negative into a column strip and the middle strip, like this one, see here. Now I have distributed this value. For example, I have calculated 140 for this location. So I need to distribute this 140 into 3 locations. What is the value in column strip? What is the value in these middle strips? And the sum of all these value will be equal to this one, 140, see? Similarly, for example, if we have m exterior positive value coming out to be 281, like which is the moment at the second location. So now I have to do the transverse distribution for this one. I have to distribute it like this one into a column strip and middle strip moment. So the moment coming in column strip is 168, and the one coming in the middle strip, half middle strip on each side, it is 112 by 2. And once you sum them, like 168 plus 112, it will be equals to 281. In the same way, you have to distribute each one is like this one. So this is called the transverse distribution. In the exam part, you may be asked for 1 or 2 to 3 locations that do the transverse distribution, for example, for the positive exterior moment, or maybe you will ask to distribute the negative moment for the exterior face or first interior support, like this is the interior support and this is the exterior face. So you may be asked to distribute only this moment in transverse direction. So depending upon the statement given in the question, you have to do the transverse distribution. Just read out these theory. I'm just going to explain you. This is the table what we will always keep looking at for doing the transverse distribution. This table is giving you the percentage of longitudinal moment, which will gonna go to column strip. On the top of it, you have the aspect ratios, which is L2 over L1. These are the values, aspect ratio. On this side, you have the location for which you have to do the transverse distribution. Because we have studied that there are 5 locations, so we're gonna see these are the statement values for each of them. Negative moment at exterior support, this is for location 1. Positive moments, it can be location 2, can be 5. Negative moments at interior supports, it will be location 3. It can be location 4 as well, because this is for interior support. So interior support, we have 2 moments at exterior face. This is for exterior face and this is for interior face. One thing to notice here is if you have to do the transverse distribution for the exterior support, then you have 3 variables involved. First variable is L2 over L1, which is the aspect ratio. The second is alpha into L2 over L1, and the third one involved is beta t. However, if you are doing transverse distribution for any other location, either it's second location, third, fourth, fifth, any other location, beta t is not involved there. You have only 2 variables involved. One is the aspect ratio, another is alpha into L2 over L1. In other ways, I can say the most difficult transverse distribution is at location 1, because in this case you have to do interpolations in horizontal and vertical directions. Another important thing to consider here, this complete one is for location 1. If you are going to do the transverse distribution for location 1, so this is the complete one. So now you will start from here. You will check what is the value of alpha into L2 over L1. If it's coming out to be 0, so you will consider these things. And if your value of alpha L2 over L1 is greater than 1, you're going to consider this one. Out of this situation, there's another distribution. You're going to check what is the value of beta t. If the value of beta t is 0, then you will further filter yourself only for this thing. And if your value of beta t is greater than 2.5, then you are going to consider in this thing. Similarly, the values here, these are for the L2 over L1, 0.5. This percentage is again 0.5, this is against 0.1, this is against 2. For example, you have calculated L2 over L1 is 0.7. So 0.7 is lying between these 2 values, 0.5 and 1. So we're going to do an interpolation to find the mid value here. This is just a theory, so just go through it. I'm just going to explain it through example. The important points, we're going to consider it over there. Now this is the solve example. Before this one, I will going to explain a few parts. The first step was calculating total factored static moment m0 for each of the 4 rigid frame A, B, C and D. Then the next second step, we distributed this total factored static moment into 5 locations. Location 1 was a location 2, then there was a location 3 and 4 at the support point, then there was location 5. This was the negative moment because it is at the support. This was the positive moment in the span. This was again negative, this was again negative, this was again positive. If you remember, these 3 values we have calculated using a case, and these are the typical values. In the third step, we have to do the transverse distribution, like we have to distribute this moment at A in this direction. Similarly, if you are asked to do the transverse distribution for moment at the location 2, or maybe you may be asked for transverse distribution moment at location 3. So once you are doing this transverse distribution, what you are basically doing, you are distributing the moment at A into what goes to a column strip, and what goes to a middle strip. In the column strip further, there's a further distribution because a column strip is having two things. First is called column strip slab, and the other thing we have here is beams. So the code says the moment which comes here, it will be distributed as 85% goes to beam and the 15% it comes at column strip slab. So previously we have seen a table, and that table was basically giving you a percentage of moment that is going to a column strip. So out of the total moment, this percentage will gonna go to column strip and the rest will gonna go to middle strip. And from this column strip you have further distribution into a column strip slab, which is a 15%, this one, and the other one, the one goes to beam, is 85%. So we're gonna see in the example how we're gonna do this whole procedure there. So coming back to the numerical, for the two-way slab with beam as described in problem 1, distribute the longitudinal moments computed from frame A, B, C, and D into 3 parts. For the longitudinal beams, so you have to find the moments which is going to beams for the column strip slabs and for the middle strip slab. These are the 3 points we need to find. So we will start with the negative moment at the face of exterior support. So we remember that exterior support means I'm doing a transverse distribution of moments for location 1. So I'm going to consider this is basically at this point. So this is in rigid frame A. I'm going to first calculate the value of L2 or L1 for this rigid frame. It is coming out to be 0.80. What is L2 and what is L1? Because you know that the rigid frame A is running here like this one. This is the rigid frame A. So every dimension in this direction, because it is running in this direction along x-axis, so every dimension here will be L1, center to center, and all the dimension in this direction parallel to y-axis, they will be considered as L2. So for rigid frame A, the center to center span L1 is coming out to be 25 and L2 is 20. So divide 25 by 20 and you're going to get 0.80. What is alpha? We already have calculated these things. Alpha for these beam, because these are, we already told you that this is the equivalent rigid frame. It is running here. So the beams here, these beams, you remember these are the T beams. So you already have calculated alpha values in previous assignments. So the value was 8.27. These are T beams. I'm just going to write here T beams just as a reference. You're going to see them in your previous example. So the next third variable is you're going to multiply these two factors, and the value is alpha into L2 over L1 is 6.61. Now the torsional constant C, because I already told you torsional constant C of edge beams in short directions, because the rigid frame A is running here and you have to distribute the moment in transverse direction. So torsional constant C is for the edge beams. This is the edge, and because you have to do the transverse distribution in this direction, and this is basically the shorter direction, that's why they have written here torsional constant of edge beam in short direction. Similarly, for a rigid frame C, which is running here like this one, your rigid frame C is running like this one, so this is your edge beam, and because this edge beam, it is running here in this direction, which is the longer direction, so you're going to see there that they have written their torsional constant of edge beam in long direction. So now just focus here. You already have calculated this torsional constant C for this beam in previous example. You can see that because this is an L-shaped beam, L-shape, and because this beam is running shorter direction, so just go in your previous lecture and see for short direction we have a beam there 12 cross 24, and out of this 12 cross 24 we have done the calculation for an L-shaped beam and a T-shaped beam. We have done calculation for both of them, so just look for this L-shape there because this is the edge beam. This is the interior one, so you'll not focus this one, just look for the edge beam. The next thing is to find moment of inertia of slab. The formula we have is BH cubed by 12. Because the equivalent rigid frame A, it is running here, so we have to consider this bit here. This is the value of B, which is very clear. It is 20 feet here, so you just multiply this 20 feet with 12 in order to convert into inches. This is H, because the slab thickness we have already given, it is 6.5 inches, so BH cubed by 12. This is the formula, so we have the value 5490. The variable beta t, this is a new term. We already have studied torsional constant C, but in the table I have showed you another term which was beta t. So it is basically equal to C over 2 into moment of inertia of slab. We already have calculated C and moment of inertia of slab. Just divide them and you're going to get the value of beta t, which is 0.98. Previously we have calculated the total factored static moment for the equivalent rigid frame A, which was coming out to be 448 kips. Then we did a horizontal distribution or longitudinal distribution for this total factored static moments. So we found these things. If you remember, we have these 5 locations: location 1, then location 2, then location 3 and 4, and then location 5. We have did all this longitudinal distribution because we are now doing the transverse distribution for the location 1. So I'm just going to focus here on this part 72. I have to do this 72 into column strip, middle strip, and beams. We're just going to note down these values. The aspect ratio, we need this one, we need this one, and we need this one. So now we're going to go to the table 2 in order to check the percentage of longitudinal moment going to column strip. This was the table what we have discussed previously. Now because we have to transversely distribute the moments at the location 1, so we're going to ignore these things. These are not more required, so I'm going to focus here myself on these things. This is for the location 1 because it says negative moment at the exterior support. So now for present case we have the aspect ratio going on here, L2 over L1. This is called the aspect ratio. For present case we have L2 over L1 equal to 0.8, which is lying between 0.5 and 1. It is somewhere here, so we even don't need these values. It is no more required because our value is lying between 0.5 and 1. Now start with this thing. We will gonna check what is the value of alpha into L2 over L1. For present case we have the value 6.61, which is greater than 0. Therefore we will ignore these things. We don't need anymore these one. I'm gonna focus here this one because we have alpha into L2 over L1 greater than 1. The value for us is 6.61. Okay, and I'm gonna move here. Now we have to see what is the value of beta t, because for present case the beta t is 0.98. It is not 0. It is lying in between here. It means I have to make an interpolation between this value, and my beta t is lying somewhere here in between them. So the value I have to consider in my table are these one. First I'm gonna do a vertical interpolation in order to find the value here, A. I'm just gonna call it A something. Then I'm going to do an interpolation of between this one and call it B. Then I'm going to do a horizontal interpolation, linear interpolation, to find the value C, which is the required answer at 0.8, because we need the value at 0.8, which is lying between 0.5 and 1. So now let's see how we can find the value C. For this we have to do 2 interpolation, one linear interpolation and the other vertical interpolation. I have just distinguished them by name as horizontal interpolation and vertical interpolation. This will be a vertical interpolation, this will be horizontal interpolation, long x-axis. So this is the concern table that I will just gonna write over there. Just note down these values. For present case, we have the value of beta t lying in between them here, which is equals to 0.98. So I'm gonna see what is the value of this percentage here and here at 0.98, because this percentage 100% it is at beta t equal to 0, and this percentage 90 is at beta equal to greater than 2.5. So I'm gonna find what is the value at 0.98, and I'll just gonna mark it at this location. Similarly, I'm gonna do another interpolation saying that at beta t equal to 0, this is 100, this is 75, so there will be interpolation which will give me a value here for beta t equal to 0.98. Then I'm gonna do an interpolation because this value here and this value here, this is at L2 over L1.5 and this value is at 1. So I need a value at aspect ratio equals 2.8 in between them. So again, I'm gonna do interpolation between them and find a value here. This value, this value, this value, and this value, these have been taken from the table which I showed you right now, and the rest of the values, these have been interpolated. So first I'm just going to tell you how you can find this value of 96.1%, because you know that when beta t is equal to 0, the percentage is 100%, and when beta t is equal to 2.5, the percentage is 90%. So what is the difference between these beta 2? I'm just gonna say it's 2.5, isn't it? Beta t is equal to 0, and the second case beta t is equal to 2.5. So the difference here is 2.5. I'm just gonna write it here just for you. This is the difference in beta t. So what is the difference in these two quantities? 100 minus 90, it will be 10%. So for a difference of 2.5 in beta, the difference in percentage is coming to be 10. So I'm going to do a interpolation here like this one. For a percentage of 2.5 difference in beta, the percentage difference was coming out to be 10%. But because our value, if you see here, the real value is we need to find the value at beta t equal to 0.98. We need to find the value here. So now the difference in these 0 and 0.98 is 0.98 difference. So I need to find at a difference of 0.98 instead of 2.5. So I'm gonna write it here like this difference in beta is 2.5, but I don't need for 2.5, I need it for 0.98. So for a difference of 1, what will be the percentage difference? Because it is multiplying here, it will gonna be divided here. The percentage difference will be this one. And for a difference of 0.98 in beta, I'm just gonna multiply both sides by 0.98. So this will become 0.98. And the difference in percentage will gonna become 10 divided by 2.5 whole multiply by 0.98. And the answer is coming out to be 3.92%. 3.92%. I'm gonna write here at beta t equal to 0, the value of percentage going to column strip is 100%. So in order to come at lower side, because once I'm going down, the value is decreasing, because at beta t, once the beta t's value is increasing, the value of percentage is decreasing. So I need to subtract this 3.92 from 100 in order to get this value. So this value is basically 100 minus 3.92, the percentage you calculated, which is 96.08 or 96.1. In the same way, you're gonna do interpolation here and find this value. Once you have determined these values, 96.1% and 90.2%, the last step is to find this percentage. I just want to explain you because previously we done the vertical interpolation. Now I'm going to do this horizontal interpolation here. So you will going to write like this is against L2 or L1.5. This is against L2 or L1 at 1. So the difference between these two values, what is the difference here? 0.5 and 1. It is the difference is 0.5. So a difference of 0.5 in L2 or L1 is bringing a difference in percentages equals to, just subtract the high 96.1 minus 90.2. The answer is 5.9%. So I'm just going to write these two figures. For a difference of 0.5 in L2 or L1 in aspect ratio, the difference in percentage is 5.9. So for a difference of 0.5, the percentage was coming out to be 5.9. But we don't need this difference. The actual thing what we require is here. If you can see here, we need the difference in these two things because actually we want this value. So the difference in these two terms is coming out to be 0.5 and 0.8 is 0.3. So I need the answer at 0.3 difference. So I'm gonna go back. I'm gonna write here, no, I don't need for 0.5. I need for 0.3. So for a difference of 1, it will become 5.9 divided by 0.5. And definitely for a difference of 0.3, I'm just gonna multiply 0.3 on both sides. It will become 5.9 divided by 0.5 multiply by 0.3. The answer is coming out to be 3.54%. So what you will gonna do, you're gonna come back here. Now because the difference is 3.54%, so you will gonna say at 0.5 the value is 96, at 1 it is 90.2. So what is the value at 0.8? Because the difference was 3.54, and you can see the value is basically decreasing once you are moving here. So you're going to subtract 3.54 from this value. 96.1 minus 3.54, it will give you 92.56 or 92.6. The answer is this one. So basically this is the percentage. 92.6% of the total moment at this location will gonna go to column strip. So 92.6% will gonna go to column strip. What moment will gonna go to middle strip is basically 100 minus 92.6. This is the moment that will go to middle strip. You can find actually this one. This is 7.4%. So all this expression has been written here. Table 1 shows the linear interpolation for obtaining column strip percentage for prescribed limits of table 2. The total moment of 72 fit kips. This moment is basically the moment at the location 1 is divided into 3 parts. 92.6% to column strip and 7.4% to middle strip. This we already calculated. Now from this 92.6%, I'm just going to show you, because we are saying that 92.6% means 92.6 divided by 100 multiply by 72. Let's see how it is, how much this one is. The value is coming out to be 66.67. I can just write 66.67. So this moment will gonna go to column strip. This moment will be further divided into 2 parts, as we already discussed, because the moment that is going to column strip is divided between column strip, slab and beam. This is column strip. I'm gonna write CS. So you have to distribute this moment into column strip slab CSS and a beam. So we already discussed that beam will gonna take 85% of this moment and 15% will gonna go to column strip slab. So I'm just gonna do this calculation for you as well. 66.67, I'm just gonna write it here. 66.67, it was the moment that is coming to column strip, and now this moment has to further divide into two things what we discuss. One will gonna go to column strip slab, another will gonna go to beam. We already have discussed that the percentage to column strip slab will be only 15% and it will be 85% going to beams. So we're going to do the calculation here. 85% of 66.67 is basically equivalent to 85 divided by 100 multiplied by 66.67. The moment is 56.67. 56.67. So this is the moment going to beam. What will be the moment that is going to column strip slab? It's very easy. You can calculate this one by just subtracting 66.67 was the total moment. So I'm going to subtract this one, 56.67. The answer is 10. So this is the moment going to column strip slab, and this is the moment going to beam, and this was the moment coming to column strip. In the same way, there are big calculation performed for other locations. For example, if you see at this part B, this is again from A, and because it's a negative moments at exterior face of first interior support and exterior face. So just remember, because these two information are telling us this is at location 3. So this is again for frame A, we have these values. So because I told you, like, the most difficult transverse distribution is only for location 1. The rest of the location, it's quite easy because beta t is not involved in those locations. So just here you just need to find L2 over L1, the aspect ratio, this alpha into L2 over L1, because it's greater than 1. So what you will do, you're just gonna highlight these value. Your alpha is greater than 1 and L2 over L1 is 0.8. So keeping in mind these two values, I'm gonna go to the table again. So because I have to distribute the moment at the location 3, so I'm gonna come here directly. I'm gonna ignore these parts, everything, because alpha in L2 L1 is not 0 for me, so this is not required for me as well. I'll just gonna focus here myself, alpha L2 over L1 greater than 1. Because my value is 0.8, the aspect ratio for my case is 0.8, which is lying between these two values. So again, this is not required for me. My value is somewhere here in between this one. So it's just a one interpolation here. I'm just gonna say that at 0.5 the value is 90, at 1 the value is 75. So I'm gonna find what is the value at 0.8. This is the percentage here. So I'm gonna do this calculation for you as well here. First, just note down the difference between these two things. In these two values, the difference is 0.5. So we're gonna say for a difference of 0.5 in L2 or L1, the difference in these two things, it is coming out to be 15. So I'm just gonna write this one over there. For a difference of 0.5, the difference was coming in percentage was 15%, but we don't need for 0.5, no, because our value is lying somewhere here at 0.8. So I'm just gonna look at the difference between 0.5 and 0.8, which is actually 0.3. Because we have the difference 0.3, so I'm gonna say for a difference of 1, it will become 15 divided by 0.5. Okay, and for a difference of 0.3, I'm gonna multiply both sides by 0.3. It will become 15 divided by 0.5 into 0.3. Now the percentage is coming out to be 9%. So we're going to go to your calculations back. So the percentage difference was 9%. I'm going to show you this calculation here. This one we were doing. This we already know. This we already know. And in order to get this value, we reached at the conclusion that I need to subtract 9% from this value, because once I'm going here, as the value of L2 or L1 is increasing, the value of this percent is decreasing. First it was 90%, and at L2 or L1 equals to 1, the value is becoming 75%. So as I increase the value of aspect ratio, the value of percentage is decreasing. That's mean the value coming out at this location, it will be smaller than 90%. So I'm going to subtract 9% from 90%, minus 9%. This was the 9% which we calculated right now, and the answer will become 81%. So 81% of the moment will gonna go to column strip, and 19% will gonna go to middle strip. This is for the equivalent rigid frame A, which has the total width 20 feet. We have calculated the column strip width and the middle strip widths, 5 feet on each side and 10 feet column strip. So this was basically the longitudinal distribution which have been performed. This is for location 1, this is for location 2, 3 and 4 and 5. The total factored static moment was longitudinally distributed here. See, this was the longitudinal distribution which has been performed previously. So now you have to do the transverse distribution right now here, that how much of this 72 will gonna go to beam, to column strip, slab, middle strip. This is basically the moment which is going to column strip, which is further being divided into column strip, slab and beams, and this is the moment which is going to middle strip. This overall value can be found using that table. The percentage will gonna come from the table, and this 5 is basically the remaining amount. You can actually find this value of 5 by subtracting the sum of these two things from 72. In the same way, if you want to find this 49, just subtract the sum of these two quantities from 255. So ultimately you have to draw this kind of table for rigid frame A, B, C and D, which will gonna show you the longitudinal and transverse distribution of moments. Once you have calculated the moments in beams, then column strip and middle strip, it's very easy to find the steel against each of them. Now this is for rigid frame B, negative moment at the face of exterior support. This is for rigid frame B at the location 1. Therefore this will also involve beta T here. Negative moment at the exterior face of first interior support. This is for location 3 and rigid frame B. The calculation have been performed here again. So you need to go through each of them and form these tables for equivalent rigid frame A, B, C and D. This is the overall summary of this direct design method. That the first step was to calculate the total factored static moment m0, which we calculated for each of the 4 rigid frame, m0 A, m0 B, m0 C and m0 D. Then the second step was to longitudinally distribute this m0 into positive and negative moments at the 5 locations. We distributed this M node into location 1, 2, location 3, and location 4, and then location 5. Distribute then moments into column strip and middle strip slab. This is basically the transverse distribution which we have performed right now. You have to distribute each of these moments in transverse direction like this one. You have to distribute this moment like this one. And while you are distributing in transverse, you are actually transferring this moment at location 1 into a column strip slab moment, a beam, and a middle strip. This is basically the overall summary. The same has been explained here. Total factor static moment is the first step to calculate. Then you're going to distribute this one into negative and positive moments. We already know that location 1 has negative moments. So here you will have 1, here you have also 3, here you also have a 4. All these have negative value. At positive location, you're going to have 2, you're going to have 5. So you're going to distribute the total factor static moment M node into these positive and negative moments. Once these have been determined, the next step is to do the transverse distribution. These moments at each side we're going to distribute into a column strip and middle strip moment. Then further in column strip moment, it will further distribute into a beam moment and slab moment. Once these steps have been performed, the next step is to find steel against each of these calculated moments.